We are ready to start. It's a pleasure to introduce Qiaoyin Pan. She's going to tell us about spinfoams with a cosmological constant.
Thank you for the introduction. And as a local member, also part of the organization, so instead of thanking the organizers, I would like to thank all the audience here for attending this wonderful conference. And it's, of course, a pleasure to present our recent work here. And as you can see from the title, in this talk, I'll talk about a spinfoam model with a cosmological constant. And this is based on the work in collaboration with Muxin and Chen Hun, who's a PhD student here at FAU. So I want to start with a statement that people often say. Spinfoam model is a covariant formalism of quantum gravity. As a formalism, we can put some criteria what a good formalism should be. So we expect that a good formalism should first semi-classically consistent with the Einstein gravity, and it should give us a finite amplitude, and it should be computable. Based on these three criteria, then we could just evaluate the spinfoam models we have at hand. So first, in four dimension, EPRL is a formalism that can reproduce a four-dimensional Regge action at its semi-classical regime. So it is, which is a discretization version of the continuous gravity. So it is consistent with Einstein gravity. When we go one dimensional lower, we have constant region model and Qiaoyin model. They also reproduce the Regge action in 3D in a similar manner. And in particular, very specially, Qiaoyin is a spinfoam model with a non-zero cosmological constant lambda. And for the finiteness, there are quantum group deformations of EPRL, and they do give finite results for the amplitude. We expect that they should correspond to a non-zero lambda, but because the semi-classical limit of this formalism is difficult to evaluate, so we still don't know. In 3D, Qiaoyin model depends on the quantum group recitation, and it also gives us a finite amplitude. For computability, EPRL is of course in the list. We've seen in several previous talks about the numerical algorithm based on the EPRL to compute the amplitude and its application to physical situation. And if you go to 3D, Ponson-Ricci and Qiaoyin model, they are based on the 6J symbols. 6J symbols are computable. So you see in this list that Qiaoyin model satisfies all these three features. And this is an example of a spinfoam model with a non-zero lambda. But this is in 3D. And in this talk, we want to go one dimensional higher. So we focus on a Lorentzian four-dimensional spinfoam model with a non-zero lambda that also satisfies these three features. Namely, it is semi-classically consistent with gravity, and it's finite, it has finite amplitude, and it is computable. So the plan of this talk is the following. I will first give an overview on how the amplitude is constructed in this spinfoam model, especially how the vertex amplitude is constructed. Then I will provide some concrete testimonies for its finiteness, consistency with GR, and its computability. I will end this talk by pointing out some future explorations. So let me start the review part. The starting point of constructing this spinfoam model is to consider the Blavatsky-host formalism of 4D gravity. It formulates gravity as a BF theory with simplicity constraints imposed. So in black, it's a BF theory with no cosmological constant. When we add the cosmological constant, then we have to add a volume term to this action. And the simplicity constraint would give the geometry encoded by the tetra to the B field. And in this action, you've seen that I put an absolute value to the lambda. Then the simplicity constraint also encodes the sign of the lambda. And there's a benefit of it. Because to construct spinfoam, the strategy is to first quantize the topological theory. Here's the BF theory. And we first quantize it to a lot of quantization construction. And when this action is independent of the sign of the lambda, which means that the quantization structure will be suitable for either sign of the lambda, and we only put the sign of lambda when we impose the simplicity constraint as the last step. So first, we want to quantize the BF theory. To do that, we consider the Lorentzian path integral of this action. Then we realize that in this action, there are quadratic term in B in this term. So there is an Gaussian integral form for the B field. Although it's just formal expression, we know that performing a Gaussian integral is the same as imposing the equation motion of this action, which relates the curvature of the condition and the B field by a linear relation. So, this means this path integral can be written as a path integral of a second term in this form, which is the total derivative. Then, when the four manifold has a trivial topology, this path integral can be written as a path integral of Chern-Simons theory on the boundary of the four manifold. The gauge group of the Chern-Simons is SL2C, and the coupling constant of the Chern-Simons theory is complex, and which is denoted by T and T bar here. By requiring the path integral to be gauge invariant, the real part of this coupling constant has to be in integer. And this real part, denoted by K here, it encodes the value of the lambda, it encodes the Planck length, and the Barbero immersive parameter. Here we just choose it to be a positive integer by simplicity. So now we realize that we need to study Chern-Simons theory on the boundary of the four manifold. And to construct this vertex amplitude, we take this four manifold to be a four ball, which is of course topological trivial. Its boundary is the three sphere. Then we triangulate it. The triangulation of the three sphere is a collection of 5 tetrahedra which are glued together through triangles pairwise. And its 3D dual is given by this gamma 5 graph. Remember that to get this Chern-Simons action, we actually use the equation motion, which gives the relation of the curvature and the B field. In Chern-Simons theory, the equation motion gives the zero curvature. But here we know the curvature cannot be zero because the curvature the curvature is generated by some geometry. And also, we realize that this equation motion is a two-form equation, which means when we do the triangulation, it's very natural to assign the discretized equation motion to the triangle, or in a dual picture, we associate it to the link of the gamma 5 graph. And what we do is the following. We first embed this gamma 5 graph to the three sphere, and then we realize that the curvature, they are just line defects on the three sphere because the curvature cannot be valuation on the line, on the links. This motivates us to consider the Chern-Simons theory on the graph complements. It means we first embed this gamma 5 graph to the three sphere and then remove it from the three sphere, and which is illustrated in this figure. Then we need to study the Chern-Simons theory on this graph complement. The solution space of the Chern-Simons theory on this graph complement is given by the moduli space of SL2C flat connection on this three manifold. And along this discussion, the punchline here is that, so we want to study four-dimensional quantum gravity with a non-zero lambda. Then it is equivalent to study a complex Chern-Simons theory on the graph complement of the boundary of a four manifold. And then we impose simplicity constraint on the graph, which generates curvature in terms of geometry. So the first thing to do is to construct the Chern-Simons partition function on this graph complement. So we realize that the discretization of this graph complement can be decomposed into a collection of 20 tetrahedra. And the partition function, the Chern-Simons partition function for one single tetrahedron is known, and it's called the quantum dilogarithm function. It is a function of the Chern-Simons space-based coordinate on the boundary of an tetrahedron. And it is a meromorphic function. Here, there's a Q and Q2 here. Q and Q2, they encode the complex Chern-Simons coupling constant T and T bar. And for a better quantization, we reparameterize this coordinate Z and Z tilde in terms of another pair of variables, which is mu and J here. Here, mu is a real variable, and J is a half integer variable, and we call it spin. From this expression, we realize that the coordinates Z and Z tilde, they are actually periodic in J. So if we add J by an integer times K over 2, it doesn't change the value for the Z and Z tilde. This means we can just choose a branch for the J, and we can choose that the branch such that the J can take 0, 1/2, up to K minus 1 over 2. So there's a truncation in the spin, and this truncation is by construction. And this truncation is implied by the lambda, because lambda and K is inverse, has this relation. So now we have, that's for one single tetrahedron. Now we have 20 of them. And the partition function for this three manifold is just, we first do the product of 20 quantum logarithm function, each for one tetrahedron. Then we will impose some gluing constraints, because we need to glue these tetrahedra together, and then followed by some series of unitary transformations. And this unitary transformation includes some Fourier transform. The result is given in this expression. And this is the result is a finite sum and convergent state integral. So this partition function is bounded. And in this figure, I want to show you two equivalent ways to represent this graph complement, or the boundary of this graph complement. First, if I remove a link of the gamma phi graph and the open tubular neighborhood, then we create an annulus. And this annulus is represented by a blue line here in this right figure. And further, if we remove a node in the gamma phi graph and its open neighborhood, it creates a full sphere, which is represented by the circle, 5 circles in this right paragraph. And what we, the key point here is that, first, and you may see this paragraph familiar because it looks like a group field theory diagram, a GFT diagram. And in fact, it can be viewed as a GFT diagram of defects on the ambient three manifold. And at the end of this talk, I will also talk about the relation of this Spinfoam model and GFT. So this, again, this is a Chern-Simons partition function I just shown, and it's a function of the Chern-Simons is a function of the moduli space of Black connection on the boundary of this three manifold. And these coordinates, mu and j here, they are actually localized coordinates. They are either localized on the annuli of the boundary, or they are localized on the four spheres. Realizing that, let's impose a simplicity constraint. Then we want to learn some lesson from EPRL. In EPRL, the simplicity constraint that imposed is the linear constraint, which states that there exists a vector in R13 such that this vector is orthonormal to all the discretized B field in a tetrahedron. Because of the linear relation of the curvature and B field by the equation motion, then this constraint can be translated to the constraint for the curvature, which is that there exists a unique vector in R13 such that it's orthonormal to all the discretized curvature for the four spheres. And this statement can be equivalent to restricting the moduli space of SL2C flat connection on the four sphere to a moduli space of SU2 flat connection to the same four sphere. So this is the simplicity constraint we want to impose on the Chern-Simons partition function. Another lesson we learned from EPRL is that first, we realize that there are two types of constraints. There are first class and second class. So the lesson from EPRL is that we want to impose the first class constraint strongly and then impose the second class constraint weakly. Firstly, the first class constraint. These constraints are imposed on the coordinates that are localized on the annuli of the boundary of this free manifold. And this constraint, when you impose it, it restricts the eigenvalue lambda here of the holonomy around the annulus, to be given by the spin. And this spin determines the area of the triangle that is dual to the annulus, or is dual to the length of the gamma phi graph. So the triangle's area is fixed by spin after imposing the first class constraints. And the second class constraint, we want to impose them weakly. To impose them weakly, we couple it with coherent states, which is peaked at the constraint surface. And this coherent state label the tetrahedron shape. Then in this figure, you see it's even more like a GFT diagram. But here, the annuli, they are addressed by spins, and the four spheres, they are addressed by this coherent state label. And at the end, the vertex amplitude is defined as the inner product of the Chern-Simons partition function after we impose the first class constraints. So there's a J here with 5 coherent states, each for 1 4 spheres. And the nice properties of this vertex amplitude are in twofolds. First, it is finite by construction, as I just shown. And second, when we take the large K limit, we find that it appears it's an integral in terms of an oscillatory action, which means we can do the stationary phase analysis. By doing stationary phase analysis, we find that this vertex amplitude, it reproduces the 4-dimensional Regic action with constant curvature in this way. So after a review, I want to show the concrete testimony for the finiteness and how this finiteness can be extended to for complex, not just for simplex. The example I want to show is this melonic Spinfoam graph. And this left figure is the 3 manifold that corresponds to this Spinfoam graph. Again, the blue lines here, each blue line represents an annulus. We can see that this figure can be split into 2, and each of them is a 3 manifold, corresponds to a vertex amplitude. And then we glue the 4 sphere x1 to 4 together. And this means the amplitude of this melonic graph can be written in terms of 2 vertex amplitude. And then the coherent state label that just the glue 4 sphere, they are shared. But we also realize that there are in red here, some pairs of annuli, they are glued together from 2 ends, and they form some tori. And each tori is dual to 1 internal triangle. So we also need to put some phase amplitude to this Spinfoam amplitude. We choose this phase amplitude to be a quantum dimension. When we take the lambda to approach 0, this phase amplitude is also consistent with the EPRL phase amplitude. So you see in this expression that first, the vertex amplitude are 2. They are both boundary amplitude, as I shown before. And we show that the integral over the integral for the coherent state label, they are integral over compact space. And also we also have some finite sums. Then this amplitude is finite. And this finiteness can be also be generalized to any Spinfoam graph just using this similar mechanism. We are also, for this melonic Spinfoam graph, we are also interested in some limit of it. In particular, we fix the boundary data, which is the spin associated to this boundary fold sphere, the 5th and the 6th fold sphere, and also the coherent state on this fold sphere. And then we consider the small lambda, or equivalently, the large K regime of this amplitude. And we also find that at this regime, it appears an oscillatory action, which means we can also study the stationary phase analysis. And we find, the point here is that the full amplitude is finite here, so we just studied its scaling behavior. We find a lower bound for the scaling behavior. It scales as k to the power 21. Then it's natural to compare this with the EPRL model, because in EPRL model, the amplitude for Melonic spinfoam graph is also considered, and it gives the Melonic radiative correction. The way to do it in EPRL is to introduce a cutoff of representation, which is J here. We introduce a cutoff by hand. Instead of summing from 0 to infinity, we sum from 0 to a cutoff J max. And then we consider a large J max limit. The true difference is the following. In the full amplitude in EPRL is really the sum from 0 to infinity. And this gives an infinite result. But here, in our result, in our amplitude, we get a finite amplitude. And the divergent behavior in the EPRL case is given numerically. And it's shown that it diverges linearly in the cutoff. Okay, let me also talk about the consistency with GR. To discuss that, we in particular look at the critical point geometry of the Spinfoam model. I've shown you part of it. First, the vertex amplitude describes the geometry of the constantly curved four simplex. And to glue the four simplexes together, we identify the boundary tetrahedra, which are also constantly curved. Then you can ask, sometimes when we glue the tetrahedra together, sometimes we form some internal triangles. Then you can ask, what is the deficit angle that is formed, that is hinged by this internal triangle? The easiest example is given by the delta 3-4 complex, and its three manifold corresponding to this Spinfoam model is shown here. It has three four simplices, and the 3 4 simplices share one single triangle, which is dual to the torus that's represented by this red circle, and we associate a spin to this torus. So we want to study to discover the critical depth angle. We study the stationary phase. We use the stationary phase analysis for this internal spin JF, and we find a similar flatness. We find a similar result as in the flatness in EPRL. So the critical depth angle is equal to 4 pi times the integer over gamma. When this integer goes to 0, then the depth angle is 0. Now, because every four simplex is constantly curved and they form a 0 depth angle, this means the 4D bulk is smoothly de Sitter or anti-de Sitter. And although I just give you one example for delta 3 complex, we did this analysis for a general 4 complex. So this result is valid for any 4 complex with internal triangles. So let me, for a summary. So the critical point geometry are the following. First, every 4 simplex is constantly curved, and the 4 simplices, they are glued by identifying the boundary constantly curved tetrahedra. And when we have internal triangle, the deficit angle hinged by these internal triangles, they are vanishing. And this means, in the semi-classical regime, the critical point of the Spinfoam model describes a 4-dimensional de Sitter spacetime or 4-dimensional anti-de Sitter spacetime, depending on the sign of the lambda. And we call it ds-ness property or ads-ness property. But if these are all the geometry that is described by the critical point of the Spinfoam model, it will be a problem. Because GR, indeed, it's not consistent with GR. GR indeed allows more geometry, but it's not a problem. Because this critical geometry is only described by the real critical points, and we can consider the complex critical point just as what is done in EPRL. Then we find that these complex critical points, they capture the non-DS geometry or non-ADS geometries. So the way to find this complex critical point is to use Homada theory. So Homada theory states that in the neighborhood of a real critical point, we can find a complex critical point. And this complex critical point describes the non-DS or ADS geometries. So after that, let me also show you how computable this Spinfoam model is. So in particular, I want to discuss the computability of this Spinfoam model, especially when the stationary phase analysis can be applied. So this is supported by two facts. First, we showed that it's the amplitude at the large K regime can be written as a finite dimensional integral with oscillatory action. I've shown you two examples. The first one is for one single for simplex, which gives the vertex amplitude. It can be written as a 40-dimensional integral. And for the delta 3-4 complex, it can be written as a 114-dimensional integral. It's finite. So we can use the stationary phase analysis. And the second point is that we observe there's a deep relation between the force simplex geometry and the moduli space of SL2C flat connection on the gamma 5 graph complement of the 3-sphere. In particular, so if you give me the triangle area and the normals of the triangles for simplex, I can fully describe the geometry of the force simplex. And we can use these geometrical data to construct the coordinates of this moduli space of flat connection, Z and Z2 and more. And with these 2 points, we can generate an algorithm. So suppose I'm giving some geometry of the force simplex. The simplest example is to consider the coordinates of 5 points in the 3-sphere or a hyperbolic 3-plane. Then I can just calculate the area and the normals of all the triangles. Using this as input, I can write out what is the Chern-Simons partition what is the phase space coordinate in the Chern-Simons theory, and these coordinates, they are the function of this geometrical data. Then using this coordinate, because the vertex amplitude is written in terms of these coordinates, so we can immediately write out the Spinfoam amplitude evaluated at the critical point, and these are the real critical point. And based on this, we can also perform some perturbation on this critical point. Then this allows us to study the higher order correction of the Spinfoam model, and they are the quantum correction of the Spinfoam model. Also, we can also do the analytic continuation of the coordinates and also the action. Then we can find the complex critical point and write out the Spinfoam amplitude, evaluated at the complex critical point. And although we haven't had a numerical package to implement this algorithm, but it is feasible, it's a concrete and complete program to calculate Spinfoam amplitude evaluated at the critical points and its quantum corrections. And also, although I just give you the force simplex geometry here and the amplitude for simplex, but using the critical geometry I just described, this can be easily generalized to a 4-complex geometry and use that to use the same algorithm to compute the Spinfoam amplitude and for a general 4-complex. Now, since I've shown you that this Spinfoam model has some nice property and is some inviting property. So let me also point out some possible future exploration. Firstly, this Spinfoam model can be viewed as a generalization of EPRL, but with a non-zero lambda. So the first generalization we can do is to consider also, so as a generalization of EPRL, we only consider the space-like tetrahedra. So the generalization we can do is to also include some time-like tetrahedra, as in the Conradi-Nibita extension of the EPRL. And secondly, we expect that there should be a quantum group representation of this Spinfoam model. The reasons are the following. First, this Spinfoam model is based on the Chern-Simons theory on the spring manifold, and we know the combinatorial quantization of transaminds gives the quantum group representation very naturally. And second, theoretical model is a 3D Spinfoam model with also a non-zero lambda. And this has a quantum group representation. We expect that our Spinfoam model can also be seen as a 4D version of a theoretical. So we expect that there should be a quantum group representation of the Spinfoam model. And lastly, based on a recent work with Muxin and Chen Hun, we find that the quantum state of a constantly curved tetrahedron is given by a Q-deformed intertwiner. It is written in terms of quantum groups. And this also motivates us that there should be a quantum group representation for this Spinfoam model. And I show you that we have the algorithm for computing the Spinfoam amplitude. We believe that it's ready to set up the numerical development for this Spinfoam model, just as it's done in the EPRL. Using this numerical tool, we can realize numerically the real and complex critical points. We can use the numerical tool to study the higher order quantum correction of this Spinfoam model. We can also apply this Spinfoam model numerically to the physical situation, especially to cosmology, because our Spinfoam model does have a non-zero lambda, and which is the case of our current universe. So we expect that applying this Spinfoam model to cosmology will give us some interesting and possibly trustful result and prediction. As a last point, I want to repeat what I mentioned at the beginning. So Spinfoam model is a covariant formalism of quantum gravity. Throughout this talk, I hope I've shown you that this Spinfoam model with a lambda is a good formalism because it's finite and it's semi-classically consistent with Einstein gravity. But there's still ambiguity because Spinfoam model, by construction, depends on the triangulation of four manifold. But we expect that a better formalism should be independent of triangulation. How do we do that? Usually, this is one of the motivations to consider the group field theory, GFT. But since this Spinfoam model is based on the transaminds theory, whose solution space is a moduli space of flat connection, so we think that it's more natural to consider the moduli space field theory formalism of the Spinfoam model, which is in analogy with the group field theory. So the way to do it is the following. We consider a field which is a function on the moduli space of SU2 flat connection on the four spheres, which carry some configuration of the tetrahedron. Then we can write a generalized moduli space field action, which has a kinetic term and potential term. In the potential term, it encodes the vertex amplitude of the Spinfoam model, and this G is a coupling constant. Although it's just an initial idea, we can already expect that if we consider the path integral of this generalized action, this should give us the finite amplitude order by order. And also, by construction, it's sum over all the triangulation, so this formalism is independent of triangulations. And with that, I would like to thank you for your attention.
Thank you, Qiaoyin. This was a fantastic talk. Questions? I see Carlo.
I just want to say that I find this spectacularly good and super interesting. This seems to me a definite step ahead in the field, having this this formulation. One question, maybe it's too general and too vague, but for a long time, people outside, Gabriele Veneziano's been always telling me, okay, you have an ultraviolet finite theory of GR. Why don't you take the standard divergences of GR in concrete examples when you have an infinite normalization and tell us how things actually normalize from the Planck scale to the macroscopic scale. You should get a finite number and tell us exactly what is. And I took the challenge, but then there were always ultraviolet divergences. I didn't know how to do that, so I never did it. But now you have a concrete way of controlling the ultraviolet divergences with the cosmological constant. So maybe there are some maybe I always say the same thing. Instead of doing more formal, is now that you have this thing, it's finite, it's GR, it's marvelous. Can we just compute some of the things that in perturbation theory of GR diverge, and have a the normalization of some normalization from Planck scale to microscopic scale, and get something finite? What would come out? That's I'm just throwing this as a challenge. But mostly what I wanted to say is that this is fantastic.
Thank you. Yes, indeed. So using this Spinfoam model, we want to construct, of course, we want to construct some physical observables. So we can just calculate, for example, if we want to consider the area operator and calculate its expression value, we can use it. We can also use this because it's a covariant formalism. We can use it to calculate some correlation function just based on this Spinfoam model. So we can calculate many observables, physical observables, using this formalism.
More questions? Surat, up there.
I'm really sorry if this is a question which indicates I misunderstood, but again, as an outsider, I wanted to understand, can you compute an S matrix where you take, maybe correlation functions and use the LSZ formula to just understand 2-to-2 graviton scattering, since you say it's consistent with Einstein gravity? Maybe just a leading tree level contribution of 2-to-2 scattering in gravity. Can we compute and match that with Einstein gravity?
I think that's use the field theory mechanism to calculate the S matrix and correlation function. Yes, we can use it because it's covariant theory, but then we can take some regime and then calculate the Spinfoam. I think the Spinfoam version of that formalism, and we need to compare with the other other results, but looking at some regimes.
But there's a very, very simple and precise answer you get for 2-to-2 scattering. I give you the polarizations of the incoming gravitons and outgoing gravitons, and there's a very specific answer that we get. Do we get the answer if we try and do it in this way, or?
Maybe I could just put something here. There have been a set of old results that in which people were involved, in which that calculation that you're mentioning was actually done, and in fact that's how the APRL amplitude came out, because these were first done with a different vertex amplitude, and the calculation came out wrong, and so that was by the Crane amplitude, and that's what motivated the correction to the APRL that gives the result right. So the 2-point function was computed, and the endpoint functions actually, which you were involved in some of these calculations, Genio, and the endpoint functions. Not the endpoint function, then the to first order, so the vertex, well, you could derive it. But then the question was, okay, fantastic, can we do loops in the sense of the Feynman? And that started to turn out very complicated. And there was these calculations of the self-energy of the gravitons, where there are the ultraviolet divergences, okay? So we didn't know what to do. But now the ultraviolet divergences are under control. So that's exactly what I was asking before. I mean, can we now do the self-energy of the graviton and just get numbers? And I expect should get, logarithm or Planck scale or something like that. But now with a cosmological constant coming in some way. So in a sense, your question is the same as my question.
More comments or questions?
I have Mike. Yeah.
Daniele.
I mean, it's along the same lines as other people asking. I mean, basically, we have to make some physical prediction to say that I got a finite answer, but then, tell me like graviton scattering or something. And I would like to know if, in fact, that also, even if you don't have the very detailed answers, what is the difference between taking positive lambda and negative lambda? It seemed that it didn't matter at all in your framework, but the physics is quite different in the two cases. So how am I seeing that? How is it going to? And also quantum corrections will be very different. And so how am I seeing that? Any hint about physical results as opposed to elegant mathematical or computational framework?
So I think maybe what you're considering is to apply it to a physical system. Am I correct?
Or ask any, scattering questions, or
So
the loop quantum cosmology for lambda equal to
yes,
positive
so,
and negative is
yes.
quite different, for example.
Yes,
So
yes, that's what I want to mention. So we can apply this to cosmology, and it will give a different prediction on. It gives different amplitude if we compare it with the EPRL, because EPRL also apply to cosmology. Then the difference is that in this model we have a Bayer cosmological constant. It can be positive, negative. They give different predictions. Then we just need to compare these predictions with hopefully with observations to tell which one is the more feasible. So we know they have different predictions.
but in cosmology, we have loop quantum cosmology in the two cases, and there are very detailed predictions that are different from each other because of the cosmological constant matters, the sign matters. So do you see any reflections there in
it's hard to tell. It's hard to tell because we really need to apply to cosmology like EPRL. They can do this only numerically. So we expect that if we also develop a numerical method, we can discover something hopefully new. So, but right now, just from this model itself, it's hard to tell.
So the DS and ADS, they correspond to two different critical points of the model. So if you, for example, if you want to study the Sitter cosmology, then you study one particular critical point. If you want to study
but physical predictions
is different.
Okay. My question was about physics that comes out, for example.
Yes, physics, and two different critical points, then the prediction must be different. Yeah. The model is there, but they have different types of
I also got confused about why is one looking only at real critical points, because if it is complex critical point, then you don't get the semi-classical answers, if I understood it correctly.
But the complex critical point is very much like what Dongxue talked at the beginning. So because when we study cosmology, it corresponds to a complex critical point, but that complex critical point is very close to a real critical point. Yeah. So here, if we study, for example, the Sitter, with cosmology with positive cosmological constant, then we start from DS geometry, the critical point with DS geometry, and do deformation to complex critical point.
Complex critical point or not? Because as you just said, for cosmology you have to use a complex critical point. This last, and then I'll stop. So are you using complex critical point in cosmology or real?
Yes, complex.
You are using complex.
Yeah, complex critical.
Okay, thank you.
Yes.
Thank you. This was excellent. I hope you can bring some of this discussion also to the panel tomorrow. Let's thank Qiaoyin again.
Thank you.
Thank you.